Hi everyone, I am Shubham Garg and welcome back to the lecture series for blockchain. Okay, so in today's lecture series, we are going to see and understand a topic that is hashing. That is, particularly, we are going to see SHA 256, that is Secured Hash Algorithm 256. All right, that we are going to see. Now, why it is in the blockchain series, you see, the blockchain uses this hashing technique to hash all the data, all the transactions in the chain of the blockchain, and for that it uses SHA 256 technique. There are other techniques as well, like SHA 512 and all. So we will be having a look at SHA 256. Okay, we will see how this SHA 256 actually works, what it actually means, and how the data is actually being transmitted in this SHA 256 thing. All right, so we will have a look at that, and we are going to see from an example, that is how it is working. So you can see here in the slides there are some examples, that is we will be hashing the string ABC and we will see how it works. All right, we will see how the hashes is generated using this SHA 256 compression function. All right, so here you can see this is the block diagram of that SHA 256. Now let me just open Paint, and we will see we will be able to understand this. All right, so first of all, some of the things that I need to tell you is some definitions, that is L here, there is this equation, that is L plus 1 plus K is equivalent to 448 mod 512. So that equation must be satisfied. All right, so let me just write it here. Okay, let me just, it is, just a second, yeah. L plus 1 plus K is equivalent to 448 mod 512, and that is actually 64. So basically this is the main equation, and now why what does it means in this equation? We will see how according to this equation this SHA 256 compression function works. Okay, this function works according to this equation. So we will see how. And now what we are going to do is we are going to take the example for that ABC example, and we will see how we are actually hashing that function. So we will have a look at that. And now first of all, L here is the length. Okay, that is for the length of the message. So L here is the length, as I told you in the slide, that L is the length. Okay, length of message. K is the 0 bits. We will see what I mean by 0 bits, and M is the message, and we will see about that as well. So first of all, talking about the length of the message. So in this case we are taking the example ABC. All right, so here there are 3 characters, that is A, B and C, and every character has an 8-bit of length, that is 1 byte. Character takes 1 byte. So the L here becomes L is equal to 3 times 8, that is because 8 bits of length, that is 24 bits. All right, since a character is equal to 1 byte, which is equal to 8 bits. So we have this L is 24 bits. All right, so it is clear till now that what is the L length. Now next thing is that we need to make sure that input should be the multiple of 5 and 2. All right, so now before that, let us also see one thing, that is this is our A, B and C. We have calculated the length like this. We can also see that when we write A, B and C, when we write them in binary, how is it represented is like this. A is represented like this. All right, B is represented like this, and C is represented like this. Okay, just a second. Yeah. Okay. Yeah, it is there. I don't know what just happened. Let me just erase this. Yeah, I will write this again. And yeah, okay, sorry about the writing. So this is how A, B and C are represented in binary. That is, these are of 24 bits, 8 bits this, 8 bits this, and 8 bits this. Okay, so this is the length in this L plus 1 plus K function. And now as according to the equation, it should be a multiple of 5 and 2. All right. So we need to make sure that the result, that the input that should be given, that is this input, that is this thing, should be a multiple of 5 and 2. All right, multiple of 5 and 2. So you see, if there is data is higher, then the length already would be greater than 24. All right, that is, length would increase as well. However, in this case the length is less. Okay, so we need to make this length, that is this 24 bit, we need to make it to a multiple of 5 and 2. That is, it should be at least 5 and 2 bits. And to make it so, what we will do is we are going to add some padded bits. All right, so we are going to basically add these zeros, and we are going to append this one according to this equation. All right, so that it becomes a multiple of 5 and 2. So that's why and that's why to do that we will be adding the number of zeros, that is the k zeros. So this is what we are going to do. And if the length have been of 5 and 2 bits, then we didn't need to add these padded bits and all. And let's say if the length is greater than 5 and 2 bits. So now let's say if the length is greater than 5 and 2. So what will happen? It is going to divide the message in the 5 and 2 bits. Like let's say the length is 5 and 4 bits. So it is going to actually divide the message like this. That is, first partition will be at 5 and 2 bits. The next partition will be having 2 bits. And we will be making these 2 bits the multiple of 5 and 2. All right. And let's say if this 2, if the length is 1026 bits. All right. Then it is going to make partitions like 5 and 2. Then again 5 and 2. And these are the sum, this when we sum this, it is 1024, then there will be this 2. So this will be made a multiple of 5 and 2 again. So this is how every bit length should be of 5 and 2 bits. All right, for the input. So now once we have our input in the length of 5 and 2 bits, what we are going to do is we are going to move towards the next step. Okay, that is, we are going to move according to the equation. So let me just do one thing. Yeah, I guess it is fine. I will just select this thing and will move the diagram downwards. Okay, I guess now it is fine. All right, so here is our diagram. And now what we are going to do is we are going to have a look at the further process. So now we have our length, that is 24 bit. Now let's move towards the equation. All right, that is, okay, yeah, just a second. Yeah, so the equation as in L plus 1 plus K, we need to make it equivalent to 448 mod 5 and 2. All right, that is, it should be equivalent to this. So when we solve this equation, what will happen? L plus 1 plus K, we will be equating it to 448 to get the value of K, that is number of zeros. Okay, that one is the appended bit, that is, we need to append this one as a single bit to the input. All right, so now L, we know that L is 24, so that is, it makes it 24 plus 1 plus K is equal to 448. So from here we can get the value of K, that is 448 minus 23, sorry, minus 25, that is 423 bits. Okay, that is 423 0 bits that needs to be appended to this message. All right, So now what will happen, that value of our L is 24, and when we write 24 in terms of binary, we need to make it to 64 bits. Now what will happen, first of all, before that, let's see that how our message is going to look like. You see, our message is in the form of, let me take another color. Yeah, our message is in the form of, okay, L plus 1 plus K. Okay, this is our message, and this length, this whole length should be that 512 bits. All right, or a multiple of 512 bits. So this should be 512. So what is L? L is 24. Okay, first of all, we are going to remove this L. All right, so now what is going to happen is that we are going to write our message, and it is in the format that is, first of all, there will be the message, that is A, B, C, and then we are going to append the 1. All right, and then we are going to append the zeros, that is K number of zeros. So that is here K zeros, so that is 423 zeros in our case, because we have 423 0 bits. And finally we will be having this L value, this L is equal to 24 value in binary in the form of 64 bits. So now how does it comes to be 64? That is because, you see, when we equate 448 mod 512, it will give the answer 64. All right, so we need to have append this the L value, that is 24, in the form of 64 bits. All right, okay, yeah, there is some lag. Yeah, so you see, it is 64 bits. So this is how, when you calculate a total this thing, you see, this is 8 bits, this is 8 bits, this is 8 bits, this is 1 bit, and this 423 and 64. When you total this thing, this will become is equal to 512 bits. So that is how our message will become 512 bits. That is the message we will be providing as the input. So now let's see what will be our final message that we will be providing as the input. So we see, first of all, there is this A, B and C, that is A, B, C. So I will write the values of A, B and C again. So it is 0, 1, 1, 0, 0, 0, 0, 1. For B it is 0, 1, 1, 0, 0, 0, 1, 0. For C it is 0, 1, 1, 0, 0, 0, 1, 1. Alright, so this is the ABC value, and then there is this 1 bit. Okay, then there will be zeros, that is 423 zeros. So there will be these 423 zeros, and then there will be the L value, that is 24 in binary terms. That is 24 in binary is basically, when we see only 5 bits, it is 11000, or we can say this 011000. This is 24 in binary, and we need 64 bits to represent that. So this is how we are going to represent, that is, these are this whole length should be 64 bits. Okay, so that is 00 till, we are going to represent it like this. It is L in 64 bits. All right, this is that 1 bit. So this whole thing is our actually the input, that is, this whole thing is our actual input, that is 512-bit input. Alright, so this is the input that we will be giving to this compression function, that is here, this 512-bit input. This thing we have computed. Okay, so we have done our first step, that is we have this input, that is our input that would be provided in this compression function. Okay, and now we will see how this input is actually being given and how it is distributed in the compression function. So this is the first part of providing the input inside a compression function. Now let me just take you back to the slides. All these things are written in the slides. It will be easier for you to understand. You see, as it is saying, the input should be a multiple of 5 and 2. We need to append 1 to the input block and add k zeros until it is 64 bits away. So we have seen A, B and C value, and then there is this one, and then there are 423 and these 5 and 2 bits. These bits are there, that is 64 is this is the length, that is 24. All right, so now next thing, this is how we have done this thing, we have done till getting the input. Now next thing is that you see our input is only 5 and 2 bits, so that gives us an advantage here. Now let's say first of all, let me just take this image again. So I will just select this. All right, so now what is actually let me just take it a bit more down. So now you see here that there is these m values. Okay, you see there is these m values and it is written in a way that is m1, m2 up to mn, like this. Okay, and when we talk about these slides, okay, let me take you back to the slides. You will see that there is something, it is written like this, like n is equal to 1 and all these thing. This thing is written like this, that is this m1, m2, mn, this is in the superscript, and in the diagram it was in the subscript. So now there is a bit difference why it is written in superscript and why it is written in subscript. So you see, when our this input is actually the m, okay, and m should be our 5 and 2 bit or a multiple of 5 and 2 bit. So when m is only 5 and 2 bit, that is our message length is only 5 and 2 bit, this is actually m1, that is m superscript 1. Okay, let me just use another color, I will use blue here. So you can see m superscript 1, this is 5 and 2. Let's say our message is of 1024 bits, then it will be divided into two parts, that is m1 and m superscript 2. Let's say it is of more parts, more length, then it will be divided into m3, m4 and so on. So in our case, we are lucky enough that our message is only 5 and 2 bits. So we just only need this one single part, that is m. All right, so that's why that is m is equal to 1. So you can see it was till mn. All right, in the slides, when you see that, let me just take you back to slides once again. See, it was m1 till m capital N, that is n is equal to 1 in our case. So that's why we only have m1, and now we will be just working on that m1. Okay, and now what we need to do is that there is the 5 and 2 bit input. However, whenever we are creating an SHA accelerator or SHA 256 compression function, what will happen, the input will never go for 5 and 2 bit. Okay, so we need to divide this into 32 bit, message of 32 bits, so that our input could be given. All right, that is, the input will be split into 32 bits, and these 32 bits are represented here, that is from this m1 to m2 till mn. Okay, now here you see this m1 to m2 till mn, these are having subscripts, that is like m1, m2 up to mn. Okay, these are having these subscripts. All right, so this is that after the message is being splitted, that is m message, that is M1. Okay, M1 is splitted into this 32 bits each, like this. So here, how it is going to split? Now when we see for the M bits, that is, it should be M0, M1, and it is going to be splitted like this, like till M15. Okay, so here it is first 32 bits, here it is second 32 bits, up till N30, like 15th 32 bits. Okay, that will make the 32 bit length. So this is how it is going to be splitted. And now once this it is going till N, because once this pass is done, that is, this will be done for M1, next again same pass will be done for M2, and again same pass will be done for M3. All right, so that's why it is going from M1 till Mn. Okay, and now we have M1, M2, M3. So this ith values of M will be given in this W register, that is, these are the word registers from W0 to W63. Okay, in these registers these values will be given, that is, W0 will be containing, W0 to W15 will be containing M0 to M15 values, and I will tell you how the other values of W16 to 63 are calculated. All right, so this is how it actually happens. First of all, we have this our message length should be 5 and 2, then it will be divided into 32 bits each. Okay, then every length of 5 and 2 should be divided into 32, that's why it is going till Mn. And once every length is divided into 32, one by one it goes towards this Mi input. All right, that is, M0 will be going to W0, M1 will be going to W1, till M15 it will be going to M15 will be going to M15, and then for W16 to W63 there will be there are different equations on how to calculate these value. We will view that in just a moment. Okay, I just need to go back to slides to show you that thing. You see, we have this M0, M1 and M15 values. Okay, so now these values are there. Now what we need to do is we need to add the values of W register. Okay, so if I yeah, before that W register, I would like to show you some of the definitions. Okay, first of all, let me just go back here. Yeah, you can see here some k values are there, k0 to k63. Okay, this is not the k0s which we used, okay, which we used in the previous equation. This is a different thing, and these are the constants. So let me just, yeah, these are the k constants, and we will see how their values are calculated, and these are the word registers. Okay, and now you see there are this A B C D F G H registers, and initially what happens after these registers get the value, that is from these compressor function, that is for W0 to W63, and this thing 63 iterations happen, and this A B C D F G H gets some value. You are seeing that this they are getting appended with this thing which is going here, and finally after getting the result, this value is again going as the input. So that means if this input here is going as the input there, that means initially some values like this should be defined. So when we go back to our presentation, you can see there is the definition for setting the initial hashes at 0. All right, so this is how we will see how these hashes, these initial values are set. Okay, so let's see. First of all, let us talk about the initial hashes. Okay, let me open the paint again. Let me just widen the area. All right, so I will do one thing. I will copy the diagram from here. So here is our diagram. So here is our diagram, and you will see that we need to set the initial hash. Okay, so here first of all, let me use paint. So initial hash, that is, okay, this diagram is not a bit visible. I will just use the original one. Okay, just a second. I will just open it with paint once again. Yeah. All right. So here is our diagram. Yeah. Now it is fine. I see. So here you can see that these hashes, it is written like this. That is h0, and it is written I minus 1, h1, I minus 2 up till h7, I minus 7. All right, like this is written like this. Okay, sorry, not I minus 7, it is I minus 1 only. Yeah, so that is I for the ith iteration. So this is how these things are written. So now what it actually means is, let me go back to the presentation. Let me show you. So you see that is, first of all, there is the initial hash, that is h0 for the initial this iteration. So when I is 1, that is for the first iteration, it becomes h00, h01, and when the iteration increases, it becomes h11 and all that. All right. So you can see here that is n is here, hash is basically computed, that is for I is equal to 1 to n, that is n is the number of blocks in the padded message. All right. So it is going to be iterated, that is for T0 to T63. These iterations are updated from A to H. Okay, so this is how these iterations happen. So now what will happen, that initially for the 0th iteration, you can see it is, the values are h00, h11, h12, h13, 14, h15 and h16. These are the initial hash values. All right, that are there up to h17 actually. Sorry, not 1, it is till h0s. All these are zeros. Yeah, because it is I minus 1, that is 1 minus 1, 0. That is, these are the initial hashes. So now there is a definition to calculate these hashes. Okay, that is, you can see these are, because these things are provided in the calculation for this input as well. There is a way to calculate these hashes. So initially these hashes are being calculated as I will just write here. It is actually the fractional part of square root of first 8 prime numbers. Okay, it is the fractional part of square root of first 8 prime numbers. Now what does that mean? Let me take an example, that first prime number is 2. Okay, so first prime number is 2. So now it is the fractional part of square root. So square root of 2 is equal to 1.41421. Okay, this is the square root of 2. Now the fractional part of square root of 2 is this. Okay, that is the 0.41421. all right. So now what will happen is that when we take this into binary, so when we take it into binary, it becomes 0.0110 1010 0000 up to so on, like this it will become. So now you see, we only need to take the fractional part, so we don't need to take this part, only this part here. And when we divide this part like this, what it becomes, this is 6, this is 9, this is 0, and up to so on. So what actual value of h0 is, H00's actual value is it's not 9, sorry, it's A. Yeah, so actual value is 6A09E667. This is the value of H00, and when we solve this we will get this value. Similarly, there are all these values defined for H0, H1 up till H7. Let me just let you all go through with that. So this is H0. When we talk about H10, this is actually something like this. This is the value, and when we go towards the H70, this is actually equal to 5BEOC 0C D19. So this is how these values are calculated. So this is how we get our initial hashes, that is H0 to H7. All right, so we get this value, and now what we need to do is we need to see the next definition, that is for the k constants. All right, so here is our diagram. You can see we have seen this H0 till H7. Now let's see the k constants, then I am going to come back to this how the data is getting towards this word registers. All right, so I will just write the definition of k constants here. This is actually the k constants is the first 32 bit of fractional part of cube root of first 64 primes. Yeah, I will just write it down. So k constants are actually the first 32 bits of fractional part of cube root of first 64 primes. So you see that first prime is actually the first prime number. We need to take the cube root, that is, for example, cube root we are taking, and then the first 32 bits of the fractional part, that is, we will be having some cube root 1 point something something or 0 point something something. So that thing is actually that fractional part, the 32 bits of that fractional part is the k0. Okay, that is the k0 values. All right, so for example, the first k0 value is actually 4288A2F98. so this is actually the value for the k constant, and that is how these k constants are created. All right, so now so far we know that how we have this k value. We have these input. First of all, we have our input, we have this k constants, we have this h constants. Now all we need to do is we need to find the way how this input is get processed, and the value is given to the w registers, that is word registers. All right, so coming back to the presentation, I know it is a bit confusing, but you see once or twice when you do with your when you do on your own, that is, try to solve this ABC example, you will be able to understand this. Okay, so we can see here that we have successfully splitted our message into 16 32-bit words, that is M0 till M15. We have set up the initial hashes, we have set up these k constants. Okay, you can see the definition, that is first 32 bits of fractional part of cube root of first 64 primes. Now we are talking about the computations, that is how these values, m values, are being provided to W63 word registers, because you see we have M0 to M15 only, and there are 63 word registers. So now what is actually happening, that is, we can see here, this is how. I will just increase the size here. Yeah, yes, I hope it is visible. Let me use draw here. Yeah, so here we have our message scheduler, that is WT. All right, so we have this WT, and now here for, as I told you, that is for 0 to 15, first 15 iterations, m value of m is equal to value of w, that is, let's say wj is equal to m of j for w0 for 0 to 15, that is j is equal to 0 1 up till 15. All right, that is the parts we have declared for the 32-bit message. M0 to M15 will be as it is in W0 to W15. Now this we have done till first 15 iterations, first 16 iterations. Now for j is equal to 16 to 63, that is the main part. That in this part the iterations are done according to this equation. Okay, you see we can tell that this is a complicated equation. Okay, so it is basically the wj value is calculated like this, that is wj will be equivalent to that of sigma 1 of wj minus 2. All right, and we can see here that below this is sigma 1 and this is sigma 2. This is actually rotation and shift functions. All right, that is, let's say we are calculating because it is for j is equal to 16 to 63, let's say we are calculating w20. So what will happen, w20 will be sigma 1 of w18 plus wj minus 7, that is 20 minus 7, that is 13, plus w13, plus we can see that it is sigma and it is sigma 0 for wj minus 15, that is w5 plus wj minus 16, that is w4. So this is how the value of w20 will be calculated, that is after calculating this whole thing. So this is how the value of wj263 is calculated. So you see we now what we will be having is we will be having the values of word constants as well. So now we have this m, we have this m processed in this w0 to w63. Okay, so we have these word registers, we have the value of these k constants. All right, we have the values of these m which is being processed here, and finally it is processed here. We have the values of h0 till h7, we have all these values. So now you can we need to get the final hash values, that is the final hashing computations. So how the final hashing computations is happening is like this. So you can see first of all that these register A B C D E F G H, we need to initialize the hash values of these A B C D E F G H registers. All right, so you can see here there are these A B C D E F G H registers, that is these registers are here. So their values will be initialized after the iterations in this word registers and k constants. So these A B C D E F G H will be getting these values, and these values will be then appended with this initial hashes that we said, and then we will be finally getting this our hashes, that is h0 to h1 up till hn. Okay, that is how we are going to get the hash. So let's see how it is getting initialized. So you can see the first value, that is initial hash value when I is equal to 1, these are initialized that is as a, b and up till h. All right, so that is h from h0 to h7 or h1 to h8, that is the same thing. Now these values needs to be updated. You can see what is happening, there are multiple iterations happening, that is once these values are getting here and added here, then again the results is getting back to this and it is getting back to this. All right, let me do one thing, I will just use another image. I will just open with Paint. Yeah. So you see what is actually happening. We have this initial ABCDEFGH values, and these values are getting here. Then we have initialized this. This is getting here, and all these values are getting us this. Now this value is again going towards this, and this is again going towards this. So this thing is happening again and again, and it is going to happen from t is equal to 0 to t is equal to 63 iterations. So how we are going to get this hash values is, let me tell you. So first of all, we have our initial hashes. This we have computed, and now for t is equal to 0 to t is equal to 63 iterations, the values of a to h is updated. Okay, so that is, you can see according to these equations, this is how the value is getting updated. All right, yeah, just give me a second. Okay, so the value is, this is how the value is getting updated. Okay, yeah, actually my display got disconnected. Yeah, it is connected right now. So coming back to this, this is how we will be updating the values. That is, you see, initially we calculated the h zeros, that is h I minus 1 when I was 1. We calculated h0 0, h0 1, all these, or as it is written here, h11, h12, all these h01, h02, these values we have calculated. So now we need to update the values, hash values, and it is by calculating a plus h1 of I minus 1. All right, that is, this is for I is equal to 1. Let's say when I is equal to 2. So what will happen when I is equal to 2? We have h21, which will be the a value. A value is h I minus 1 1, that is h11 plus this hi, this value will be this a value plus h11 again. So this is how these values are calculated. Similarly, up till h8 we will be calculating these values. All right, so basically this is how the values are calculated, and it will be running according to the equations. I will show you the equations, that is for t is equal to 0 to 63. These hashes are running according to the t equations, and all these a b c d e f g h values are also getting updated. I have not included those equations in these slides. I will just write it down for you. So what is actually happening? For basically these are the equations, that is for t is equal to 0 to 63. So this is somewhat happening like this. T1 will be equal to h plus sigma 1 to 256. There will be e and chi functions which we are using. We are not going to go into the detail of these functions. That's why I have not included the equations in these slides. So you can say this is how T1 is calculated, till we need to calculate the T2, that is for sigma is equal to 0 to chi, and major functions also we are going to use in this. Okay, and that is major function ABC. And for t is equal to 0 till t63, these equations will run, and it is also going to update the values for ABCDEFGH. So h will be, it is going to update in the fashion like h will be G, it will be F, F will be E. Alright, E will be equal to D plus T1. Similarly, D is equal to C, C is equal to B, B is equal to A, and A is equal to T1 plus T2. So this is how this whole thing t is equal to 0 to t is equal to 63 iterations will work. And now finally, after doing that, what h values we will be having is like this. Let me just increase the size of this paint. Yeah, so finally we will be having, as we can see, we have h0i is equal to a plus h0i minus 1. Similarly, h1i is equal to b plus h1 of I minus 1. Similarly, we are going to have h7 of I, which is equal to h plus h7 of I minus 1. So this is how we have, and to get the for our final hash, what we will be having is, we are going to having hn, that is for the iterations, nth iteration. This h0 will be appended with h1, will be appended with h2, with h3, up till h7 basically. So we will be having h4 of n, we'll be having h5 of n, h6 of n, and h7. So this will be our final 256-bit hash that is generated. So each of this is 32-bit. Okay, so this is how our, and whole this is 256-bit. So that is how our final hash is basically generated. So you can see here in the diagram, that is here we have this h0 to h1 to h7. This is basically going to run, it is hi0 hi1, it is actually for the nth iteration, that is hn01 hn this up till hn7. So that is how we finally generate this 256-bit hash. So I know it can be confusing sometimes. It is basically, if you are wondering from where all these definitions come from, these definitions are actually in the Ethereum white paper handbook. That is how the Bitcoin Hashcash system, proof of work system works. This is actually in that mentioned in that handbook, and it is also mentioned that why these things we need to have these things for 32-bit each. Actually, when the hardware is designed, it is defined using 32-bit registers. So that's why it is like this. So let me just do one thing. I will just show you that handbook. Okay, and I will put the link in the description as well. So just let me open the book once in one moment. So I have just paste the URL, I have opened it, and it is opening. So just give me a minute. So this is actually the handbook which is giving the description for SHA 512, 256 and 384. Okay, so here you will see that example as well. All right, so here you can see this is the introduction. Here it is the operations of hashes, that is we've seen how we have passed it into 5 and 2 bits. Again, this is the description of SHA function. You can see these, we have used these things in the equations, that is we have used these bitwise OR and these rotation and shifting operations in those equations which I have written, and this is how you can see the initial h0's hash values, that is we have seen in our example also it is 60 and something like this. So this is the initial hash values. Similarly, we will be pre-processing. You see here is this ABC example. All right, so basically we are appending our example like this only to make it 5 and 2 bit. You see we are following all these steps. We have initialized the hash. You can see these are the equations for j is equal to 0 to 63. These equations I have shown you for chi and major functions. Okay, and we will be computing the intermediate hash to finally get this hash. So this is how this hashes work, and you see if you want to see the definitions of this chi and major functions and sigma functions, these are the definitions. And we have seen that this is how this W values are getting updated for 16 to 63 and 0 to 15. And these are the values of K constants. You see we have seen one of the K constants here, and this is these are the 63 K constants. This how now when we see the compression function, we are seeing that we need for 32-bit inputs. Why we need 32-bit input? This is basically cleared by this diagram. You can see there are these registers. These are 32-bit each, except 32-bit input, and also the modular addition that we use is 2 to the power 32 addition. All right, so that's why we basically need to divide it into the 32 bits. And you can see there are some of the final results for hashing ABC. Okay, so after padding, this is what actually the message becomes, and the final hash value is this for this ADC or ADC function, ABC function. Okay, so this is actually the final result, and you can see all these details which are present in this handbook. You can see here it is showing all the iterations, that is hash of ABC. All iterations it is showing what is happening for t is equal to 0 to 1 to up to t63. So you can see this is how iterations are there for t63. and these are the initial hashes value, and it is getting updated with the initial hash values. Okay, we have seen h1 was a plus h0 like this. So this is how it is getting updated, and you see final value is actually the appending this thing. Okay, that is we have appended this thing, whole thing is the final value. Similarly, it has shown the iterations for calculating the hash of this whole thing, and all. Next you will find the SHA 512, that is almost same as well. There are some differences however. So this is all available in this Ethereum handbook, and I will be pasting this link for this Ethereum handbook in the description. I hope it is clear how the SHA 256 value is calculated. You see, because generally what happens, we are not able to understand how these hash are calculated. We just use hashing so much in our daily life that this hashing word, that we only know the definition, that it is just going to reduce the length of data, but how the length of data is reduced and how on the hardware level the computations are happening. You see, basically here we have seen the algorithms only, but when you see that this diagram, this basically shows you shows a bit about the hardware representation of that hashing. You see, because there are some these registers A B C D E F G H registers, and these functions, these computation functions are added. So this needs to be created on the hardware level, all these things, so that the final hashing can be done. So this is how the process of hashing actually looks like. If we see the hashing process in the depth. So this is all for this video. We have seen one of the concepts of blockchain, that is SHA-256 hashing, and in next video we are going to see the Muckle root tree concept. So this is all for this video. See you guys in the next video.